Hey everybody, it's Mr. Ray here with our next lesson in grade 12 vectors. We're currently working in the unit regarding the equations of lines and planes. On the previous lesson we looked at equations of lines in R2, and we looked at something new called the vector equation, and from that we created the parametric equation. So those were brand new, and those were ways of defining a line in R2 using vectors. We're going to continue on with lines in R2. We're going to be talking today about the Cartesian equation, and this should seem very familiar to those of us who've taken previous math courses. So before we get there, just wanted to do some definitions here. This one here, the direction vector, this is what we've talked about previously, and we used it to actually as part of our vector equation. It's a vector, and the name we give it is little m, vector little m, and it has components which we usually call little a and little b. So this is basically it's a direction vector, and it tells basically the slope of the line in R2 that we're talking about. Okay, so it doesn't necessarily have to be the line, but it's parallel to the line that we're talking about, that we're defining with the vector equation. Now, from the direction vector, we have another vector we're going to start using today called the normal. Now, the normal is a vector drawn from the origin perpendicular to the given line. So since this is perpendicular to the line, it's also perpendicular to the direction vector. So normal and direction vector always are perpendicular by definition. And we call the normal, because it starts with n, vector n, and we give its components capital A, capital B, which are different than these, but they will be related, as we'll see in a few minutes. Okay, and we're going to be using the normal to actually create our new equation, quotation marks, called the Cartesian equation. So we're only talking about R2 today, so x and y axes only. So the equation of a line in R2, Cartesian equation of a line, is given by ax plus by plus c equals 0. And that should be familiar because that's what that defined a line in grade 9. We called it the standard form of a linear equation. It's exactly the same format. Okay, but now we're going to relate it to vectors. Okay, so that's really where we're going with this lesson. Now, some of these things we're going to sort of discover. So let's look at these two here. Two lines whose normals are n1 and n2 are parallel if and only if one normal is a scalar multiple of the other, and that kind of goes by definition. This is also true of direction vectors. If you had two different lines with two different direction vectors, those lines would only be parallel if one of their direction vectors is a scalar multiple of the other. So that also applies to the two lines normals. Okay, and again, this one's also true. Two lines whose normals are n1 and n2 are perpendicular to each other if and only if the dot product of the two vectors is equal to 0. And we know that's true because if the dot product is 0, the two lines meet at a 90-degree angle. Okay, this is also true of the direction vectors. They're only perpendicular if the dot product of the two direction vectors is 0. And here's our old friend, this formula to calculate the angle between two lines. And this came from when we were taking the geometric perspective of the dot product. The original formula was A dot B is equal to magnitude of A times the magnitude of B times the cosine of theta, which is the angle between them. So all this formula is dividing both sides by magnitude A, magnitude B, and you've got cosine theta equals this expression, and then you just take the cosine inverse to get the angle. So we're actually going to use this on one of the examples today, just to find the angle between two lines. Okay, now we've already noticed the parallel between the Cartesian equation, which was ax plus by plus c equals 0, back to grade 9 when we did equations of lines. Now if we look at it, if we relate vectors with slope, this is a nice little exercise here. So if you had this direction vector AB, sorry, the direction vector is down here. 0 or OC is the direction vector for this line here. Now if we looked at the components of that direction vector, the components are A, B. Okay, so what the A means is that's the change in the x direction, and B is the change in the y direction. In other words, rise and run. Okay, so if I know the direction vector, I can actually calculate the slope, because it's going to be B over A from the direction vector. Okay, and one thing we never mentioned before, I can actually, with a vector equation, I can actually define a line that's totally vertical by using a direction vector that has an A value of 0 that says there's no run, but there's a rise, or rise up or down. So I can actually define a vertical line using vector equation, but I can't do it using the slope y-intercept form, because I'd have a run of 0, which if I divide by that to get this slope, it's undefined, right? So that's what this is talking about. Okay, so there's another parallel back to grade 9. So let's try a few things out here. Okay, so we're going to create a Cartesian equation of a line. Do a few steps to lead up to that. So we've got these 2 points A and B with those coordinates. We want to write the equation of the line passing through A and B. First, we're going to use vector and parametric equations, and then I'm going to introduce something new called symmetric equation, which is directly from parametric. Okay, so for the vector equation, and again I'll use the letters VE for vector equation. If I look at those 2 points, I can see, well, I can get a direction vector from those 2 points, and that direction vector will be equal to the change in the x's, which would be 5 minus 1, which is 4, and the second component is 8 minus 3, which is 5. So I know the direction vector that's used between those 2 points. I also know two position vectors that go to 2 points on that line, because they gave us A and B already. So the vector equation is going to be pretty straightforward. I'll just write it as this. So I can take my pick of a position vector either to A or B. I'll pick A. So the position vector to A would be 1, 3. That's a vector, not a point. And then I do the scalar multiple of the direction vector. So plus t times the direction vector 4, 5. Okay, now the parametric equations. Okay, so remember we got that directly from the vector equation. We just look at the x component and the y component as separate equations. So x would be 1 plus 4t, and y would be 3 plus 5t. So that's from the previous lesson, nothing new there. We're just getting some practice in. But now we're going to create something called the symmetric equation. So I'll actually write this out since it's the first time. I realize I didn't do the definition of that. I'll just show you through this example how it works. So symmetric equation. So the way this works is I take each of the parametric equations and I isolate for the variable, which is my scalar multiple. So in this case, I'm going to rearrange this first equation for t. So if I do that, the first thing I do is subtract 1 from both sides. X minus 1 equals 4t, and then divide both sides by 4, and I get t, because I'm isolating for t, is equal to x minus 1 over 4. And if I do the second equation, same thing. Isolate for t, I get t equals y minus 3 divided by 5. So you can see both of these equations are equal to t, which means I can set them equal to each other. So this is what the symmetric equation is. It's x minus 1 over 4 is equal to y minus 3 over 5. So here is the symmetric equation, and you can see how we built that from the parametric equations, which we built from the vector equations. So all these have a natural flow to them. You basically start with vector equation, build your parametric equations, and then your symmetric. And you can actually work backwards. I'm not going to be doing that today, but I could hopefully give you the symmetric equations of a line, which would allow you to create the parametric equations, which would then allow you to create the vector equation. So they're all very closely related. Now, our goal here is to do the Cartesian equation. So what was all this stuff we were doing here? Well, from the symmetric equation, you can directly create the Cartesian equation, and this is what I mean. So if I just rewrite, it says using the symmetric form, so I'm going to start with what I wrote here, x minus 1 over 4 is equal to y minus 3 over 5. And now I'm just going to try to write this in the form ax plus by plus c equals 0. So the first thing I'm going to do, multiply both sides. I could do cross multiply, or another way of thinking that, multiply both sides by 20. Either way, I'm going to get 5 times x minus 1 is equal to 4 times y minus 3. Okay, and then we're going to expand. 5x minus 5 is equal to 4y minus 12. And now I'm just going to rearrange that. So I want the x and the y on the same side, so I'll move everything over to this side. So it's going to be 5x minus 4y. And then we're going to add 12 to both sides, so that's going to give me a plus 7 over here. Okay, and here is the Cartesian equation. Okay, so that's one way of getting the Cartesian equation, is to start with the symmetric equations, symmetric equation, and then basically do your cross multiply and rearrange and get it that way. But there's one thing we want to point out here, and this is where this is going, is bringing back the concept of the normal vector. So this is just a refresher from what we talked about in the definitions. A perpendicular to a line is called the normal. Find the normal vector from our line above. What do you notice when comparing the normal vector to the Cartesian equation? Well, if I go all the way back up here, if you remember, the normal vector was m equals 4, 5. Now, so the normal, and we did a little bit of this. We know that the direction vector, if we did the dot product with the normal, we would get 0. So we did a little bit of this exercise previously. So if you remember, how do we do this to get, we basically want to get a line that's perpendicular, and that's the normal. We use basically the negative reciprocal, which is something we learned in grade 9 as well. Negative reciprocal, we just flip the numerator denominator of the slope and then set it to the opposite sign. So we did the same thing previously, and the way we did that was we just flipped the positions of this vector, the direction vector. So I would write a 5, 4. So that's the reciprocal part. I just flip the the two components of the vector, but I didn't do the negative part yet. So what I do now is flip one of these two signs, not both of them, just one of them. So you really have your choice here. I could make that -5, keep that as a +4, or I could keep that as a +5, make that as a -4. So in our case, and you'll see why in a minute, we're going to try to keep the first component of the normal positive if you can. Okay, now if we go back and we compare, if we compare the Cartesian equation, if you look what we have here, we've got 5x minus 4y. Well, that 5 minus 4 seems very familiar, and that's actually the normal, and that's not a fluke. This is always going to be true. Okay, so think about it. Well, these two vectors, if we do the dot product, I'll just show this instead of talking about it. M dot n equals 0, and that's definitely true if we do that. That means they're perpendicular, which normals and direction vectors are. Now we're going to call this, we called the normal, we gave it the components capital A, capital B, and from here we can see that A is equal to 5 and B is equal to -4. And if you go back and look at these, they are, that's we call that ax plus by plus c equals 0. Well, there's the A, there's the B. They come directly from the normal. So that's going to be the quicker way of getting a Cartesian equation, is to, well, it shouldn't be too hard to find a direction vector from the original line in vector equation form. So use that direction vector, flip it around, make one of the components the opposite sign. That gives you the normal. And once you have the normal, you basically create the first two parts of the Cartesian equation. Now, what it doesn't give you is that C part. So in order to figure out what C is, we're going to be doing that here. We're actually going to have to plug in a point that we know is on the line, just like we did back in grade 9. Okay, so now the last part is basically doing what I just talked about, develop a Cartesian equation of the line through 4, -1 with a normal of 3, 5. So we don't even have to do the negative reciprocal. This is the normal. So we know that from here that A is equal to 3, B is equal to 5. So I can take those and build most of my, well, I'll start off with the generic equation. And now I'm going to change A to 3, B to 5. C stays the same for now. And, well, they gave us this point 4, 1. So A4, so 4, -1. I'm going to plug that in now. So the x is 4, so 3 times 4, plus 5 times y, which is -1, plus c equals 0. Okay, so that's going to be 12 minus 5 plus c is equal to 0. And if I move these numbers to the right side, well, that's going to be a 7. If I subtract 7 from both sides, I get c equals -7. And from that and this, I can just update my c value with what I just discovered here. So that's 3x plus 5y minus 7 equals 0. Okay, now this just so you're not comparing back to the previous and saying, well, that's not the right equation. This was a different line than this one. Okay, this had a different normal and it had different points. So the fact that these are close but different really has no bearing on this question at all. Okay, so you can see we basically discovered two ways to make a Cartesian equation of a line. One is to start with the symmetric equations and just rearrange. And the other one was to get the normal of the line and a point, and that's all we needed. That's all we had here. So sometimes they don't give you the normal. Sometimes Sometimes they might give you the direction vector. Sometimes they might just give you 2 points. So if they just gave you 2 points, well, what you could do is find the direction vector from the 2 points and then get the normal from the direction vector by doing the negative reciprocal and then using one of the points to plug in, and you could create the Cartesian equation from that. Okay, so let's keep moving forward. So example 2, this is definitely a throwback to grade 9 because the question says, determine the equivalent vector and parametric equations of the line y equals 3/4 x plus 2. And, well, sorry, that's not the right. Well, that's the slope y-intercept that we learned in grade 9. So we're going to take that form of a line linear equation and we're going to create the vector and parametric equations from that. Okay, so how do we do that? Well, we have 2 pieces of information from this. We have the slope of the line and we have a point on the line. It happens to always be the y-intercept. Still a point though. So we'll start with the slope. So m equals 3/4. And from that we're going to create the direction vector m. Notice how that's a vector and that's just a value. But it's directly related. So we know, and if you forget the order here, think about rise over run. Rise is the y component and the run is the x component. So my direction vector will be 4, 3. Very important that you get the right order or throw everything off. So that's your direction vector. And I also have a point 0, 2. So I can create a vector. Well, let's just put 0, 2 so we remember what it is. So I can do a position vector. I'll call it R0 is equal to, same as that, so 0, 2. So I've actually got from this slope y-intercept form, I took the slope. From the slope I created a direction vector. I took the y-intercept, turned it into an actual xy point, and then I created a position vector to that point. And that's all I need because now I can just create my vector equation. Maybe I'll just put my VE here. So a vector equation is R equals, and then I start with my position vector. So 0, 2. And then the scalar multiple of the direction vector, 4, 3. Okay, so that should make sense. I mean, we just reinterpreted what the slope meant in terms of a direction vector and used the y-intercept as our position vector. So now that we've got our vector equation, we can create our parametric equations by doing an equation for the x component and doing another equation for the y. So x is equal to, so in this case it's going to be 0 plus 4t. I don't have to write 0 plus, I can just put 4t. And the y would be equal to 2 plus 3t. Those are the the parametric equations. Okay, so you've seen an example converting slope y-intercept equation into a vector equation for a line. Okay, so the third example for the line with this vector equation, determine the equivalent slope y-intercept form. So we're doing the exact opposite of what we did up there. So let's start with the direction vector, the direction vector is here. So that tells us that direction m, the direction vector, is equal to -1, -4. So now we just kind of do the opposite of what we did here. We convert the direction vector back into a slope m. So if you need to remember again, use the, it's going to be rise over run. And which one is the rise? Well, it's the y component. So in this case, the rise would be -4, the run would be -1, Well, we can simplify that, change it to positive 4. So we know the slope is 4, so that tells us that our equation so far is y equals 4x plus b. Okay, what do we need to get b? We need a point that's on the line. Do we have a point that's on the line? Yes, we do, from the position vector. So we're going to use the point 3, 6. I'll just call it p for point. And we're going to plug it in here. So that means y is 6, x is 3. So 6 equals 12 plus b. So that tells us b is negative 6. And now, well, we just plug in the value of b that we just got back into here. So y equals 4x just minus 6. Make that nice and clear. 4x minus 6. And there's our slope y-intercept equation, which we created from the vector equation. So these are opposite processes. Okay, one last thing we're going to do, and that I said we actually calculate the angle between two lines. So that's what example 4 is looking at. Determine the acute angle formed from the point of intersection, formed at the point of intersection created by the following pairs of lines. Now, if you remember, the equation that was on the previous page was that angle between the two lines is equal to, well, we're going to do cosine inverse of, and on the top we've got the dot product of two vectors, and then divided by the magnitude of the two vectors. Okay, now let's go back to these equations of lines. Now you can see the way they do it in the textbook. If you're working with more than one line at a time, they give it a subscript with the capital letter L. Tells you it's a line, line number 1, line number 2. Okay, and we'll do the same thing later on with planes. Okay, so this just keeps track. It's not part of the equation, it's just an identifier for the equation. Okay, so how do we know what vectors we're talking about here? Well, the good news is I don't really have to find the point of intersection of these lines. All I really need is the direction vectors. And in fact, these position vectors don't matter at all. So I can kind of ignore them, and I'm going to focus on these vectors. I'll call them A and B, just because I called those A and B. So if I did, I need to get A dot B. So if I said, well, A is the first direction vector, negative 1, 3, and B was the second direction vector, 3, 4. So then A dot B that's going to be negative 3 plus 12 is equal to 9. And while I'm at it, I might as well do the magnitude, so I can just plug everything in. So the magnitude of vector A, remember how we do that? It's just like Pythagorean theorem. It's this squared plus this squared, square rooted. So that squared is 1, that squared is 9. So the magnitude is square root of 10. And for the second one, magnitude of B, we've got 3 squared plus 4 squared, that's 25. We take the square root of that. Well, the square root of 25, which is nice because that's just 5. So now when I plug in all this information I just did, I get theta is equal to cos inverse of A dot B, which is 9, over the product of the two magnitudes, so that'd be 5 root 10. Okay, and if I do this on a calculator at this point, I get theta is equal to 55.3 degrees. So therefore the angle between L1 and L2 is 55.3 degrees. And just one little note here. Did you notice they said determine the acute angle, which kind of implies, well, it could mean that there's more than one angle. And that's really what we're talking about here. Because when I have two lines that meet, okay, so that's hypothetically those two lines. When I talk about what angle do they meet at, well, there's two possible answers. There's this angle here, which is acute, and there's this angle here, which is obtuse. Okay, but we do know that both of those angles add up to 180. So when I did my cosine inverse, I got the acute angle. There's also another angle, if I subtracted this from 180. So I think that's like 124.7. That would be the second angle, but of course that's obtuse. So they kind of clarified we only want one angle, not the obtuse and not both of them. Okay, so that's where that comes from. You might be asked to find the two angles, or maybe the obtuse angle that the two angles meet at. And so the cosine inverse would only give you the acute. You'd have to just realize I get the obtuse angle by subtracting this from 180. Okay, so that's how we create Cartesian equations for lines in R2. So hopefully you see the connection back to grade 9. There's plenty of them, but you also see the connection between the Cartesian equation and the vector equations and how we make use of the normal vector. Okay, so that'll be it for today. Hopefully that made sense, and we'll see you on the next lesson. Take care.